Whereas in the shell method, we're usually rotating about a vertical line. 1 second here. Okay. Oh, I guess while we're waiting, it's probably worth mentioning that the first midterm is exactly 2 weeks from today. So it'll be the Friday after next Friday. So there's still a decent amount of time before the first midterm, but just so that way it's on your mind a little bit. Like you're starting to think about it. Okay. I don't know exactly what I'm going to be putting on the first midterm yet. It'll probably be going up to section maybe like 7.1 or 7.2 or so. Whatever, like it'll cover whatever is up to next Friday, pretty much. So whatever the week after next Friday, there's not going to be, it's not going to be on the exam. Okay, so where were we? We were doing the shell method. And I guess one way of thinking about the shell method versus what we already learned with the disk method, when we were doing the disk and washer method, if you remember the formula, it looks something like this. The volume was given by pi times the integral times f of x squared. You can think about this as being pi times r squared, where r is the radius from the x-axis to your graph. So you should be thinking in terms of like the area of a circle. With the shell method, you should be thinking in terms of circumference. So this is the equation we were working with on Wednesday. So it's not exactly the circumference, but it's kind of close, right? We have the 2 pi r, like 2 pi times the radius gives you the circumference of a circle. And then we just need to make sure we multiply by whatever the height of the shell ends up being, which is given by f of x. Right, so the idea was, it's all encapsulated in this single image, or I guess these 3 images, where if you choose some point xi, the radius is given by this quantity. Right, it's the distance from the origin to this point xi. And then the height is given by this point here, which is f of x. So we look at this line, and then this is given by the height, which is f of x. Right, so it's important to remember this when we start looking at more complicated examples, because we're not always going to be rotating just about the y-axis. And we're not always going to just be looking at like f of x. We might have like a difference in 2 functions. And so we went through one example. I didn't really draw the picture. I just applied the formula that was given to us, and it worked out fine, right? So we wanted to compute the volume of the solid obtained by rotating the region under the graph of this function, some cubic function over the interval from 0 to 1 about the y-axis. And so the key thing here is we're rotating about a vertical axis. So that means we want to be doing the shell method, or at least like our functions in terms of x, and we're rotating about a vertical axis. So we want to be using the shell method. And so you just apply exactly what's given to you inside of this formula. So the volume is given by 2 pi times x multiplied by f of x, where f of x is the function that was provided. You just multiply things through, apply the power rule, and like once you have the setup, integrating usually isn't that difficult. So this is where we finished on Wednesday. Just to show an image of what's happening here, I feel like having an image helps. So we're starting off with this graph, and the graph looks something like this. We're only interested in the graph on the region from 0 to 1. So we're starting at x is equal to 0 to x is equal to 1. If you plug in x is equal to 0 into this function, you just get y is equal to 1. And if you plug in x is equal to 1 into this function, you end up getting y is equal to 0. So you get this point here. So the graph looks something like this on this region. And you can plug in intermediate values to kind of get the shape, but the cubic function, so it kind of has like a wacky shape a little bit, right? It's not completely straight. And so what we're doing is we're rotating about the y-axis like this. And so the shape that we end up getting, it's kind of like an onion that's cut in half. So it looks something like this. Right, so we have like this 3D shape that we obtain by taking this region about the graph and then rotating about the y-axis. And so this is the volume that we ended up finding. Okay, any questions? So this is like what we did on Wednesday, right? Any questions before moving on? Okay, so just like with the disc and washer method, we'll look at more complicated examples. This is kind of just getting your toes wet. And so instead of just looking at a region bounded between, say, like the x-axis and your function f of x, you can look at a region between two different graphs. So we're going to assume we have two different functions, f and g, and we're going to assume that f of x is greater than or equal to g of x. And so now we're going to think in terms of like, what is the radius going to look like and what is the height going to look like? So the radius is going to be, it doesn't really change even though we're looking at two functions, right? So the radius is still going to be this x, right? This is still the radius. It's the distance between the origin and wherever your cross section is. The only thing that's going to change is going to be the height. So instead of just having f of x as your height is now going to be f of x minus g of x. So this is the height. And so this is reflected in the equation in the following way. So like this first equality isn't any different from what was on the previous page. But what changes is like, what is the height of the shell? So the height of the shell is now going to be f of x minus g of x. And so that's what's reflected here. And so let's look at the next example. For the next example, it wants you to find the volume V obtained by rotating the region enclosed by the graphs of f of x is equal to x times 5 minus x and g of x is equal to g minus x times the quantity of 5 minus x. And so before drawing the picture, let's just find the points of intersection. That will determine the limits of integration we're looking at. And so what we're going to do is we're going to set the two functions equal to one another. We're going to say that x times 5 minus x is equal to g minus x times 5 minus x. And so I would recommend multiplying things out and simplifying. If you multiply these terms out, you end up getting the function 5x minus x squared. And this is going to be equal to 8 minus 5x plus x squared. And so we want to solve for x. And so how we can do this is we can move everything on the left-hand side over to the right-hand side, or vice versa. It doesn't really matter. So this is going to be 0 is equal to 8 minus, actually, let's do things, I like doing things in terms of like the highest power. So this is really equal to 2x squared minus 10x plus 8. You can divide both sides by 2 because you don't really want the 2 in front of the x squared. So this implies we have 0 is equal to x squared minus 5x plus 4, which you can then factor as x minus 4 and then x minus 1. Right, so the 2 points of intersection are given by x is equal to 1 and x is equal to 4. So I'm not always going to provide you with the graph, so it's important that you know how to do this. And so those are going to be 2 points of interest for us. So we have x is equal to 1 and x is equal to 4 are the 2 points of intersection. And then from there, you can plug in some points to kind of determine what the shapes are going to be. We have two parabolas, one's facing downwards, because we have the minus x squared. The other is facing upwards because we have the positive x squared. So you should end up getting a graph that looks something like this. So just by looking at like x times 5 minus x, you can see this graph will have zeros at x is equal to 0 and x is equal to 5. So it looks something like this, like this downward facing parabola. So this is the graph f of x is equal to x times 5 minus x. And then the other graph that we have is this 8 minus 5x plus x squared. This is an upward facing parabola, and it's going to look something like this. It's not perfectly to scale, but just getting the general idea down. So I'm drawing it in green. What really matters is that you know they intersect at x is equal to 1 and 4, and that on this region we have f of x is greater than g of x. And so this green function is our g of x, which is equal, I'm going to write it in terms of like the like expanded form. So this is 8 minus 5x plus x squared. And so we're taking this region and then we're rotating it about the y-axis. And so we end up getting the following shape. It's what's called a torus. So it's going to look something like this. So this is the cross section. Again, you don't really have to visualize this part, but I'm just doing it for the sake of it, I guess. Okay, and so once we have all of this information, we have that the height of this region is just given by f of x minus g of x, and then the radius, like we're rotating about the x-axis, so the radius is just given by x. So that means that our volume, this is going to be equal to 2 pi times the integral from 1 to 4 of x multiplied by the difference of these two functions. And so this is going to end up being equal. So I'll write it out in this way first, and then I'll simplify, just to make sure everything's clear. Right, so this is going to be like parentheses. We have f of x minus g of x. So this is going to be like this x times 5 minus x subtracted by this 8 minus x times 5 minus x dx. And so if you simplify, like you combine like terms, multiply things out, you end up getting this is going to be minus 2x cubed plus 10x squared minus 8x. Right, all we did really, like we already, when we're solving for x, like to find the intersections, we're already kind of subtracting one function from the other. When I was solving for x, I really just did g of x minus f of x. So we ended up getting the following equation. If you flip the order or like how you're subtracting things, you just end up getting like minus 2x squared plus 10x and then minus 8. And then we're multiplying all of it by x. So that's why the powers are increasing. Again, I'm just doing algebra, so like you should be able to do this on your own, and then you can check and make sure that you end up getting this. And so once you're in this form, it's just a matter of doing integration. So the integral here isn't too difficult. You just use the power rule. So this is going to be minus 2 over 4 times x to the 4th power. So it'll be minus 1/2 times x to the 4th plus 10 over 3 times x cubed. And then you'll have 8 over 2 times x squared. So that's going to be minus 4x squared. And then you evaluate from 1 to 4. And so if you plug in these numbers, like x is equal to 4, and subtract what you get when you plug in x is equal to 1, you should end up getting that this is going to be equal to 45 pi. So it really isn't that different from the disk method we were doing on Monday and Wednesday. The formula is just a little different. I haven't handed that out yet. I will recently. Yeah. Any questions about this example? Okay, so as long as you can keep track of like the radius, so the distance from the origin to whatever your cross section is, like this x, and then the height, like you should be able to set up the integrals correctly 100% of the time. And on the exam, I'm more interested in making sure you know how to set up the integral than I am in the actual computation. So you'll get good credit as long as you know how to set things up. Okay, so for this next example, it's another shell method. This one's a little bit different in that now we're going to be shifting the vertical axis in which we're rotating our solid. So for this one, I want you to use the shell method to calculate the volume V obtained by rotating the region under the graph of f of x is equal to x to the minus 1/2 power over the interval from 1 to 4. And so now the axis is about x is equal to minus 3. So maybe like work on this one. Try setting up this integral for the next 5 minutes or so on your own or with people around you, and then we'll go over it together. So just try setting this thing up over the next couple of minutes. And if you have any questions, just raise your hand and I can help. Okay, so let's start going over the setup for this problem. So if you want to look at the setup for this problem, the first thing I would recommend doing is just graphing the picture or the graph that they give you. So this one, it only gives you one graph. We're just looking at the graph of f of x is equal to x to the minus 1/2 power. You can rewrite things in the following way to make life a little bit easier for you. So x to the minus 1/2 power, this is the same thing as having 1 over x to the 1/2 power, which is really just the same thing as having 1 over the square root of x. And so we're on the interval. At least we're looking at the values of this function on the interval from 1 to 4. So it's going to look something like this. So we're interested in the region from 1 to 4. For this function, f of x is equal to 1 over the square root of x. And so the first thing we can do is just plug in x is equal to 1 and see what the value ends up being. If we plug in x is equal to 1 into 1 over the square root of x, you just get 1. And then if you plug in, oh, let me actually graph the point. So we get the point 1, 1. If you plug in the point x is equal to 4, you get 1 over the square root of 4, which is equal to 1/2. So you get this point. And so the curve is going to look something like this, like just connecting the dots. And so we're interested in the area underneath this region of the graph. So this region here. And so what's different about this problem versus the problem that we had before is the axis of rotation is about x is equal to -3. So I'm just going to draw this vertical line. This is the axis of rotation at x is equal to -3. So this is what we're rotating about. And so now if we take a random cross section in our region, so we're just going to label this point as some random point x that lives between 1 and 4, and we draw this cross section. Again, the two things we're interested in are the radius and the height. So like the radius is the distance from the axis of rotation and x, and then the height is the distance from the x-axis and your graph. And so with our axis of rotation being x -3, I guess I'll ask you, like what changes? Like what do we have to adjust inside of the integral that we're going to be looking at? Does anyone know? Yeah, we're going to make the radius bigger. How much bigger? Yeah, it's going to be +3, right? So if we're looking at the radius is kind of the combination of the distance between x is equal to -3 and the y-axis, along with the distance from the y-axis to x, right? So like the total radius we have, maybe we should use a different color, do orange. So this is the radius. Again, it's the distance from x is equal to -3 to x. And so you can view this as two smaller distances. Really, we have this distance of 3, and then we have this distance of x. And so the radius is going to be equal to x +3. And you can view this as just being, like, if you really wanted to find the distance, the formula is just given by x minus -3. So that's where like this x +3 comes in. And then we also have, I mean, the height isn't really the hard part here, right? We don't have two functions. We just have like the single function. So we have the height. This is just equal to f of x. And so now we have that the volume, once you know what the radius is and the height, it's just a matter of plugging in to this formula, right? So the radius is now going to be x +3, and then the height is just f of x, where f of x is equal to x to the -1/2 power. So we have that the volume, this is going to be equal to 2 pi times the integral from 1 to 4. Okay, so what changes here is now instead of having an x, we're going to have an x +3. And then we're multiplying by the height, which is going to be this x to the -1/2 power. So I go between like x is minus 1/2 and 1 over the square root of x. When you're integrating, it's easier to write things out as x to the minus 1/2. So you can just think in terms of the power rule. Before I continue, are there any questions about how I set up the integral or how this is set up? Yeah, question. It doesn't give you, like, we don't have a g of x in this situation. So like in the previous example, it gave us like a function f of x and it gave us a function g of x. So in this case, we had two different functions and it explicitly tells us we have f of x and g of x. For this example, it just gives us f of x, so you don't have to worry about a g of x or anything like that. Yeah, another question. Why is radius x always in the middle? It doesn't have to be in the middle. It can be, I just do it because it creates the most space. Like this is just like a random point x on the interval. So if you really wanted to, like your x could be right here, like right next to the 1. The key thing to remember is x is a variable, so it can change, right? So instead of like having like x drawn like this, x would be drawn, it'd be a little bit shorter, but it's still denoted by x. Like we're just, like x is going to vary from 1 to 4. So it can be any random point in the interval. Is this for like illustrative purposes, really? Okay, any other questions about the setup? Okay, and so at this point, once you have things set up, like on the exam, if this is a 5-point problem, it's probably get you like 3.5 points, maybe 4, undecided, but it's like the bulk of the points, right? Okay, and so once you have this, you just need to multiply things through, solve the integral. So this is 1 over 4, x times x to the minus 1/2 power just gives you x to the 1/2 power. Then this is plus 3 times x to the minus 1/2 dx. And so now you just use the power rule. And so this ends up being equal to, so if you're doing the integral of x to the 1/2, it's x to the 3/2 power over 3/2. If you're doing something over 3/2, it's really just the same thing as doing 2 over 3 times x to the 3/2 power, right? If you took the derivative of this function, you would have 3 over 2 times 2 over 3, so they cancel out. And then you subtract 1, so you get 1/2. And then if you're doing x to the minus 1/2, finding the antiderivative, you add 1. So it's going to be to the 1/2 power, and then you divide by 1/2, which is the same thing as multiplying by 2. So this will be plus 6 times x to the 1/2 power. And then you integrate, or you're evaluating from 1 to 4. So then you just plug in these numbers, and this ends up being equal to 64 pi over 3. And on the exam, you can leave your answer like this. Okay, yeah, so it really isn't that bad. Like as long as you draw the picture, kind of organize all your information, you know how to like plug into the equation, it really isn't that bad. You just have to keep track of the radius and the height. If you keep track of those two things, you can do any one of these problems, really. Okay, any questions about this example? Yeah, go ahead. You don't have to draw the picture. Yeah, I think like the picture helps. Like the picture could serve as partial credit. Like if you get the setup wrong, but I kind of see like your picture and where your thought process is, I can give you extra points. But if you don't draw the picture, but you still know how, like, and it's x is equal to minus 3, so we're shifting the radius by 3. Like you can go right to this step if you want to on the exam. Any other questions? Okay, I think I'm gonna skip this next problem. This is like another, it's like similar to the last problem we did on the disk and washer method. So in this example, it's like use the shell method to compute the volume V, obtained by rotating the region in the first quadrant between y is equal to 9 minus x squared and the x-axis. So it wants you to use the shell method to rotate about the x-axis. So you're going about a horizontal axis. And so like how this goes is you write things in terms of like x is a function of y. I kind of want to skip this because like in practice on the exam, if you're rotating about the x-axis, you're just going to use the like disk method instead of using the shell method. So I wouldn't really ever want you to use the shell method in this situation. So I'm actually going to just skip this one. I have one other handout that covers section 6.3 and 6.4. We'll just have time to go through maybe like 1 or 2 examples. But this could be good review for the exam if you want additional practice in section 6.4. And these notes are online as well. If you have your tablet, you can just find them on campus. But there's kind of more difficult examples in this one, and one that I want to look at in particular. So in the first page of these notes, I'm really just outlining like when you want to be using the disk method and when you want to be using the shell method. Does everyone have the notes before I start talking? Okay. Yeah, so the first page, I'm just outlining like when you're using the shell method versus when you're using the disk and washer method. You should be associating the shell method with rotating about a vertical axis, say like the y-axis. And you should be associating the disk and washer method when rotating about a horizontal axis. One way of thinking about this is you can think about like when the cross section is perpendicular versus parallel to the axis of rotation. So for instance, if you have a curve like this, and this is your cross section, and you're rotating about a vertical axis, say like the y-axis, because the cross section and the axis of rotation are perpendicular to one or parallel with one another. Maybe I should put in the words. So yeah, parallel cross section with axis of rotation. I wasn't planning on writing it, so that's why it's so crammed right now. What this means is you're going to be using the shell method, right? So you just take a point, you have like a vertical cross section and the axis of rotation is vertical. So they're parallel, which means you want to use the shell method. If we instead are doing a horizontal axis of rotation, it looks something like this. So thinking about the exact same curve again, the exact same cross section, except now we're rotating it about a horizontal axis. You can see that the cross section and the vertical, the cross section and the axis of rotation are perpendicular to one another now. So if it's perpendicular, then you want to be using the disk / washer method. That's one way of thinking about things. So on the exam, I'm not always going to say like use the disk method or use the washer method. You have to determine the best method yourself and then go from there. And so this is really all you have to know. Just know the relation between the cross section and the axis of rotation, whether or not they're parallel or perpendicular. And then I outline like a different way of thinking about things as well. But I kind of want to just go on to examples. So these are the two equations we've been using in terms of just having like a function f of x. Of course, things change a little bit if we have like f of x and g of x, right? We do f of x squared minus g of x squared in the disk method. Then we do f of x minus g of x in the shell method. Okay, so the example I wanted to outline is actually a couple pages. I think it's this example, the one at the bottom of page 11. And I think in your notes, the ones I handed out, I actually draw the picture for you. So I guess I shouldn't spend that much time talking about how this picture is drawn. So the picture looks something like this. Wait, did I draw the picture? Okay. I'm debating. Oh, it's page 3. Okay, yeah, I have yeah. Okay, so it's page 3 in your notes. I'm like forgetting I guess like my notes are kind of like online, my notes are a little bit crazy. Sometimes they're like part of a longer attachment, sometimes they're on their own. Okay, so the picture looks something like this. So we have two graphs, x squared minus 1, which is a parabola facing upwards, starting at y is equal to -1. And then we have another graph, 2x minus 1. So this is a line with slope 2 that starts at -1 as well. And so it turns out that these 2 points are going to intersect one another at x is equal to 0 and x is equal to 2. This is something you can find out on your own pretty quickly, just by setting these two functions equal to one another, solving for x like we've done in previous examples. And so this is going to be x is equal to 2. And so we have something that looks like this. It's not perfect, but this is just like the, I'm going to emphasize that this is a parabola a little bit more. Okay. So we have like this parabola. This is given by x squared minus 1. And then we have this purple line, which intersects the parabola at these 2 points. And so this line is 2x minus 1. And so we're looking at this region here. So the reason why I wanted to emphasize this example is the axis of rotation is given by y is equal to 4. And so the axis of rotation is above the two graphs that we're looking at. It kind of looks ambiguous. I can't tell if that's a y or a 4. So y is equal to 4. Okay, so if we want to find the volume of rotation, do we want to use the like disk / washer method, or do we want to be using the shell method here? Yeah, we're going to be doing the washer method. If we take an arbitrary cross section, I'm going to erase the red markings here. If we take an arbitrary cross section between x is equal to 0 and x is equal to 2, it's going to be perpendicular to the axis of rotation. So if this is our x, this is x, and this is the cross section. If we continued the cross section, it'd be perpendicular to the axis of rotation. So this means we're going to be using the washer method. So we want to use washer method. As cross section is perpendicular to axis of rotation. Okay, and so if we're doing the washer method, we need to find 2 radii. The first radius is going to be like the inner radius, and then we have the outer radius as well. So the reason why I wanted to highlight this problem is, I guess, like intuitively, at least looking at like area between curves, when we're thinking about subtracting 2 functions, we always think about doing whatever function is above the other function. So in this case, you would be thinking we do 2x minus 1. Well, I guess 2x minus 1 squared minus x squared minus 1 inside of the integral. But it's all relative based off of the axis of rotation. So if you actually draw what these radii are going to look like, the shorter radius is going to be the radius that begins, or the distance that begins at the axis of rotation and then goes down to 2x minus 1, right? This is the shorter distance between the two. And so I'm going to label this red line. This is Rn, like the inner radius. And so this inner radius is really just going to be 4 minus 2x minus 1, right? It's like this distance here. So this is going to be equal to 4 minus 2x minus 1. This is the same thing as having 5 minus 2x. And then the outer radius is actually going to correspond to the smaller curve, like the curve that's beneath the line that we have here. So this is going to be the outer radius. So that's this line that goes down here. I kind of drew it overlapping with the cross section. That's just a coincidence. I just wasn't careful enough. But the outer radius, this is going to be 4 minus this x squared minus 1. So this ends up being equal to 5 minus x squared. Right? So you shouldn't be thinking in terms of which function is above the other function when determining which radius is larger than the other. It's all relative based off of the axis of rotation. So if we want to find the volume of this region rotated about this, like y is equal to 4, axis of rotation, it's going to look like the following. So the volume is now going to be equal to pi times the integral. So the points of intersection were 0 and 2. So we're going from 0 to 2. And so we're going to be doing 5 minus x squared minus 5 minus 2x squared inside of the integral. So it's really like this function subtracted by this function after adding or subtracting by 4. Or subtracting 4 from those functions. Right, so this is, I mean, I've been saying this, but this is like our out. You always do the outer radius subtracted by the inner radius. Okay, so now it's just a matter of multiplying things through. I don't like doing the disk and washer method because you always have to like square things out. So it's like a decent amount of computation. This is like pi times the integral from 0 to 2. This is 25 minus 10x squared plus x to the 4th power minus 25 plus 4x squared. Oh wait, I skipped one. Would it be minus 20x? Yeah, minus 20x plus 4x squared dx. I'm gonna run out of space. Let me add a page here. Okay, and then from here, it's just a matter of combining like terms. So this is going to be pi times the integral from 0 to 2. This ends up being equal to x to the 4th power. Then you have minus 14x squared. And then you have plus 10x, right? Or hold on. Oh, wait, no, it's just plus 20x. And then plus 25. Because we don't have an x term here. We just have like the minus 20x, and then we have a plus 25. Oh wait, no, we have a plus 25 and a minus 25. Okay, so those terms cancel out with one another. So you should end up getting this. And then from here, it's just a matter of using the power rule. So this is pi times the integral from, we're actually doing the integral now, so we don't need to write it out. So this is x to the 5th power over 5 minus 14 over 3 times x cubed plus 10x squared. Then you evaluate from 0 to 2. So it's just, you just have to plug in 2, right? If you plug in x is equal to 0, everything goes to 0. And so this should be equal to 136 pi over 15. Okay, so this is an important example to remember. Problems like this, there'll probably be one example like this on the exam where I try and trick you in terms of like, you have to make sure that you have to keep track of like what the inner radius is and the outer radius is. Like, it's not just because, like, you can't just choose the outer radius to be whatever function is larger than the other function. Okay, any questions about this example? Okay, so that's why it can be helpful to draw the picture. If you draw the picture, it's kind of clear, like which line is longer than the other, right? You don't have to do any like algebra or anything like that. Okay, we'll go through one more example and then we'll end class. Let's just do the next one. I don't remember how this goes, but it should be fine. So for this one, I want you to use any method to find the volume of the solid obtained by rotating the region enclosed by the curves y is equal to e to the minus x squared over 2. And then it's just y is the other function you have is the exact same, except you multiply by minus 1. And then we're going from x is equal to 0 to x is equal to 1. And we're rotating about the y-axis. If we're rotating about the y-axis, what method are we using? Yeah, we'll be doing the shell method. We have like the vertical axis and our functions in terms of x. If you drew a picture and looked at the cross section, you'll see the cross section would be parallel with the y-axis. And again, I think I just draw the picture for you or give you what the graph looks like. For this example, I'll just do like, I mean, you graph it as you would any other function, even though you have like the exponential functions, which maybe makes it look scarier than it actually is. So we're going from 0 to 1. If you plug in x is equal to 0, you get e to the 0, which is equal to 1. Similarly, if you plug in x is equal to 0 into this, you'll get minus 1. And then if you plug in x is equal to 1, you get e to the minus 1/2 power. Or yeah, you'll get e to the minus 1/2 power. So it looks something like this, something like this. So the graph will look something like this. So we're interested in this region of the graph. And it wants us to, we're taking this region about the graph, and then we're rotating about the x-axis. And so we're not really, or the y-axis. So we're not really doing anything fancy with the radius. Like we can just choose a random point x. This would be like point x here. This is a random point x between 0 and 1. The axis of rotation is the y-axis, so we don't have to add anything to x. It's like the radius is just equal to x here. And then the height is going to be the difference between these two functions. So this upper function is e to the minus x squared over 2. The lower function is e or minus e to the minus x squared over 2. So we have that the height, this is equal to e to the minus x squared over 2, subtracted by minus e to the minus x squared over 2. So it's really just the sum of these two things. So this is like e to the minus x squared over 2 plus e to the minus x squared over 2, which you could write as 2 times e to the minus x squared over 2. And so the volume equation will look something like this. I'm gonna rush a little bit. So we're doing the shell method. So the volume is going to be the form of 2 pi times the integral from 0 to 1 of 2 times e to the minus x squared over 2 dx. I'm going to bring, oh, I need to multiply by x, right? So let me erase this. Because we're doing the shell method, you should be thinking in terms of circumference. So you always have like the 2 pi x. And then you multiply by the height. So this is times 2 times e to the minus x squared over 2 dx. I'm going to bring the 2 outside of the integral. So this is really just the same thing as 4 pi. And so if I wanted to solve this integral, what technique should I use? Anyone see? Yeah, we want to use substitution. I guess it's, you don't have to do this if you don't want to. You might be able to see what the integral is without using u substitution, but you have like e to some function of x. So using u substitution is a good idea. We'll let u be equal to minus x squared over 2. So then du is equal to minus x dx, which is really the same as minus du is equal to x dx. And I guess we're changing the limits of integration, right? If we're using u substitution, we should be plugging in u is equal to 0. So if you do u of 0, this is just equal to 0. If you do u of 1, this is equal to minus 1/2. And so the integral looks something like this. I might go a little bit faster. So this ends up being minus 4 pi times the integral from 0 to minus 1/2 of e to the u du. Again, what you could do is you can switch the order of these limits of integration, and it has the effect of getting rid of the minus sign. So this is the same thing. Let me move this out of the way. This is really the same thing as doing 4 pi times the integral from minus 1/2 to 0 of e to the u du. This is just equal to 4 pi times e to the u evaluated from minus 1/2 to 0. And then if you plug these numbers in, you should end up getting that this is going to be 4 pi times 1 minus e to the minus 1/2 power. So I kind of went quick towards the end. But again, like the interesting part is setting up this equation in the first place. So what's done on the left-hand side of this example. And again, the solutions to this will also be online as well. So it could be good practice. If you want additional practice in these two sections, you can go through the remaining examples and find the solutions on Canvas. Any questions about this? Okay, so on Monday, we'll pick up in section 6.5. Oh, and I usually go like the first 10 or 5 to 10 minutes in class on Monday, I'll go through some homework problems. So if you have like particular problems you want me to go over, you can ask me in class on Monday.